Hey guys, this video is first of all long overdue, so excuse me for that, but there's a very good reason why it is. This machine, this goddamn machine, I've been working on this for over a month. And the reason for that is that, believe it or not, it's very difficult to work out the kinks to tune this machine properly in such a way that it runs smoothly. And the reason for that is because it runs off of encoders. So all the motors that are in this machine for the X and Y and Z axis have encoders on them. And because of that, if you don't tune them correctly, then the machine just doesn't want to run. It gives you errors. But it wasn't just that. It wasn't just that. It was a multitude of problems. And I'll go over that as I get more and more into this. But first of all, I just want you to see that it draws and that it's working.
So here, I'm just using the keyboard to jog the y-axis to insert the paper right now. Funny enough, the paper itself is the y-axis because, you know, the machine moves the paper up and down. And I'm just setting it into place for the homing. And after that's done, I adjust the z-axis and put the pen all the way down on the paper so it's touching. So now in the LinuxCNC software, what I'm doing is homing the X, Y, and Z axis. And then after that's done, I click play and it prints out an image. Sometimes it's a little hard to get the tolerances right. I had an issue with this machine that the Z-axis would skip a few steps every time it raised the pen, which ended up making the print grow fainter and fainter as it went on. And to fix that issue, I just lowered the speed of the Z-axis. You can change the speed in the configuration files. So it was almost done with this print, but I decided to put more downward force on the pen while it was still printing, and I ended up causing an error during the print, and so it stopped the whole thing. This is how it turned out, but you get the point. It prints pretty well. Before I even got to printing this picture, you have to print a even object, like a square. It could be even a circle, or I did a star, and you have to make sure that every side is equidistant, and that way you know for sure that your proportions, your X and Y proportions are correct, and then you can move on to pictures.
Before I even get into how I built this thing, I just want to go over the previous robots that I built, because I've built two previous robots that ran off of stepper motors. And for the record, I do not recommend building a drawing robot purely based off of encoders for your first project. You should, if you're doing this for the first time, you should honestly stick with stepper motors because they're way easier. So for any beginner trying to start off with CNC, I fully recommend going this miniature route, taking apart a CD or DVD drive and looking for those drives that are controlled by stepper motors. And you'll know that they're stepper motors when you see them because they have that long screw and they have 4 wires. There could be 6 wires as well, but usually they have 4 wires. When I first started playing around with these CNC machines, I started off with this one. I built this first and I started playing around with it, and it taught me a lot about both the hardware and the software. And the stepper motors were really simple to play around with. And if anything does happen to the motors or the axis on this machine, it's easy to swap out parts or find new parts because it's just from a CD or a DVD drive, so it should be fairly common. However, with the bigger machines, it's a much different story. So that's why I recommend going the smaller stepper motor route. You don't necessarily need to even use Arduino to control this. In my case, I did. I used Arduino to control this, but I don't think you need to. You can actually control this machine via the parallel port, like I'm doing with this one, as long as you have a motor controller like this. And this motor controller is an L298N motor controller. It can control 2 motors, and it provides a 5-volt output for the encoder itself, and that's why I kind of like it in my encoder machine. So funny enough, I stress that I want beginners to start off with this machine when I myself didn't start off playing with a machine like this. I actually started building this machine first. Yeah, I built this wooden frame. I scavenged some metal dowels from printers. I cut copper pipes that would fit over these metal dowels on either side to make an axis to move. And I scavenged all my stepper motors from printers too. I used an Arduino Mega to control these easy drivers over here to thus then control the steppers to move everything. And then for my Z-axis, I used another stepper motor controlled assembly from a CD drive. That worked out okay, but I had a lot of problem with keeping everything stiff as hell. Look how wobbly that is. That's not acceptable at all. So after finishing this one and understanding both the hardware and the software for the stepper motor control thing, I moved on to this one, and I put all the electronics on, and I made a drawing robot out of it, and it worked. There was a lot of issues with keeping it stiff, and it was kind of wobbly, but it worked all right. This was originally supposed to be a DIY 3D printer, but I never got there because really the issues with it not being stiff, it's just no. I wasn't gonna deal with that, and it was a bad idea to make it a 3D printer with that amount of wobble. It's just not gonna work. And then after this, I kind of wanted to see how I could control motors with encoders. Now this is an important jump because whenever I take apart a printer, I always see these motors, the motor assembly with encoders on them. And I never really understood how to interface with them. I never understood how to control them. And so I took it as a challenge to create a robot, a drawing robot like these, that is solely controlled by encoders. And I did it, but I'm telling you that you need experience with both the hardware and the software side of things before you get to this project.
Starting out, I located the encoders for the X and Y axis because I needed to attach wires to them. You only require 4 wires. 2 wires are for powering the LED and the sensor, and the other 2 are for carrying the signal out into the computer's parallel port. Before I reattached the sensors, I always made sure to power them with 5 volts and check on an oscilloscope to see if they were working correctly. If you don't have one, a multimeter on its DC voltage setting can also tell you if you're getting a signal from the sensor. I'll go over the specifics of how I wired the sensors later into the video. Another problem that would prevent me from getting good prints was this piece of metal that sat right under the original print head. It was used to just support the paper as it was being printed onto, but because I was replacing the print head with a pen plotter, it needed a smooth surface under it, and so I needed to replace this piece of metal with a custom cut one. Another thing to note is that I'm giving new life to a printer that would otherwise be thrown out and or scrapped for parts. The fact that most of the assembly for the X and Y axis is already there for you and has a decent construction that will provide for accurate prints was a big convenience that shouldn't be overlooked when you are looking to build such a machine. Next up was figuring out the hardware for the Z-axis. I used a pre-built assembly from a CD drive and removed everything on it except for its sliding carriage components. With pliers, I managed to wrap around 2 springs similar to those that you would find in a click pen, so the carriage would always want to slide down. Be careful of how much force you are putting on the carriage because the motor controlling it has to overcome it and hold it in place. Next, I cut out a sheet of metal from just some scrap I had and began to shape it into the pen holder. When you are doing this, it might be different if you want it bigger or smaller. All this process is just trial and error, shaping it, looking to see if it fits how you want it to, and reshaping it. The point is to have enough room for a bolt and nut to squeeze the pen against the cartridge and keep it in place. I also make sure to try and use any existing mounting holes on the carriage because drilling new holes into this brittle plastic can be tricky and may cause it to crack or break. To mount this assembly on the printer itself, I hand sawed a slot for it to slide into on the x-axis and slightly widened the slot with a piece of metal that was heated by a torch, melting the plastic. Now that I knew everything fit, I carefully worked out how to connect the Z-axis motor to the carriage so it would be able to control it. I cut out a better shape for the motor and with just 2 screws managed to secure it on the top right of the carriage assembly. The motor was set up as a worm drive and connected to this gear, which I used to my advantage because it stuck out and would be able to lift the carriage by just a thin wire.
So because the Z-axis is being controlled by this motor that has an encoder on it, I wanted to take the time to explain how you would find the pinout for the encoder. So first off, you have to look at where the encoder is exactly, and then follow that on the back side. And then so you see that one side of the encoder has 3 pins, and the other side has 2 pins. Now the light emitting diode that is within this package that actually shines through all these holes and through on the other side to the sensor has only 2 pins. It's a light emitting diode and therefore it has 2 pins. And so right away you see 2 pins over here. So that's a dead giveaway. But now you don't want to put power across this just yet because you don't know which one is positive and which one is negative. So one way to figure out the polarity is to just look around the circuit board, and right away you see that one of the traces that is connected to one of the leads on this LED goes around over to these capacitors and these resistors, and this trace touches all of them on one side. And generally, not always, but generally, it is highly suspicious of a trace when it does that, when it connects to a lot of things in a line or at once. It is suspicious of being ground. But there is a better way of testing this. If you don't have a multimeter, then you're going to have to look at the PCB for context clues and just look at the surroundings and figure out which one would have a high percentage of being that ground, or the positive side or the negative side. So since this is a light emitting diode, and keyword is diode there, we can use the multimeter and have it on the diode setting. So once we have the multimeter on the diode setting, you can simply put those leads across this diode and check for certain which is positive and which is negative. Alright, so I'm going to go ahead and connect to one side of the leads, and nothing is happening, so that means this is the incorrect polarity. I turn it around and I connect to it again. There you go. Now, because we have a reading, that reading is actually the forward voltage drop of this diode, and because we're getting that reading, we know that this is the correct polarity of that LED. And as far as the sensor pins go, usually you just figure out what to connect to via trial and error. Usually what I do is connect to the middle lead and then connect my other wire to one of the other leads and start out from there. If that doesn't work, I either switch them around or I connect to another lead and just try it out. And another thing to keep in mind here is that when you're putting power across this LED, you have to make sure to limit the current. If you burn this LED out by just directly connecting power to it, then you're screwed because you can't use this encoder anymore. So usually what I do is I look for the resistor that's connected to this LED, and it looks like this one right here is connected to it, and I figure out its value, and I either use this same original resistor on the PCB to connect power through to the LED, or I go to my own collection of resistors and try to find a very close value to this resistor. If for any reason you can't figure out the value for the resistor that you want to use, generally speaking, 100 ohms to 500 ohms is fine as a range.
I didn't want to make anything too permanent, so I secured both sides of the Z-axis with strong springs and had no issues with this design. Now you may notice that the motor I'm using here is different from the final Z-axis motor I decided to use, and there's a good reason for that. The main issue was that the smaller motor had a smaller encoder and was outputting a smaller signal, resulting in LinuxCNC and the computer to not recognize that the motor was moving. All my other encoders were outputting 3.3 volt signals, while the small encoder was outputting close to 1.5 volts. Not nearly enough.
So I've tried at least 3 or 4 different combination of things, including op-amp configurations and transistor amplifier configurations, to try to amplify the signal coming out of this encoder that controls the Z-axis motor. Now obviously you can see the difference between the two discs here, and the problem occurs when I try to connect this encoder over to LinuxCNC. It just doesn't provide a big enough signal, well, enough amplitude, that is, to satisfy LinuxCNC and make it recognize that the motor is indeed moving. And so I think for the sake of my patience and my effort and time, I'm just going to move on to this other motor, and that I know for sure works. But I just want to express the differences between these two, and the fact that LinuxCNC doesn't seem to like the motor on the right, or the encoder on the right here. So if you're going to use a motor like this, that outputs a smaller signal than 5 volts, then be prepared to maybe order a chip that specifically amplifies the digital signal coming off that encoder, or maybe experiment with your own transistor or op-amp amplifiers, because you're going to need to amplify that signal so LinuxCNC could recognize it. I think I'm going to revisit this topic later on in the future, because I really want to understand how to properly amplify the small signal coming off of this motor so it can work with the machine.
I cut the plastic frame again to make space for the new motor and had to file down the surface it was to be mounted on. Once the motor fit and meshed with the gear pretty well, all it took was one screw to secure it in place. Now we can talk about the software side of things. Familiarize yourself with going into the configuration files, because if you need to adjust an axis speed, change or look up pins, or change any other values, it's going to be in those files. To create a new axis, which would be the Z-axis in this case, I copy and pasted a lot of the code. When I got any errors, I would look them up, change some values or code, and try to run the program again. Eventually, after a lot of code, I had LinuxCNC recognize there was a third axis. Now, you don't have to do all this. I'll provide the configuration folder in the description, and once downloaded, all you have to do is overwrite the existing etch configuration folder, and you can change any values necessary for your setup after you do this. At around this time, I noticed a problem I overlooked. I noticed the parallel port on the motherboard simply didn't have enough pins to support a third axis. I thought about this before, and because of my research, thought I could simply configure the port in such a way to make certain pins outputs and certain pins inputs. While that's true to some extent, none of the options available satisfied my requirements, so I ended up buying a parallel port PCI card. I got a NetMos card because I heard they were plug and play, and I didn't want to have any driver issues.
So for the configuration that I'm setting up, I need 9 outputs and 6 inputs in total. And on the regular DB25 parallel port, all of these pins are bidirectional. However, in LinuxCNC, it only supports certain configurations, and the parallel port can be configured as an output and provide a total of 12 outputs and 5 inputs, which I can't use, and it can be configured as an input and provide 4 outputs and 13 inputs, but I still can't use that. And it can also be configured in this X mode, which allows a more flexible mode with 8 outputs and 9 inputs, and that is still 1 pin off from what I need. And so really, with all these configurations that are offered, none serve me well to control 3 axes to make this machine move.
I'm sure anyone that can program the configuration files well could figure out a way to use the remaining few pins on a single parallel port to control a switch connected to, for example, a solenoid that could move the Z-axis up and down depending on an off or on signal. That's just my idea anyway. In my case, I needed to add a second parallel port to have a fully working motor on the Z-axis.
So on the official LinuxCNC page, it will tell you how to add a second parallel port. And so according to this, all I need to do is first go into the terminal and type in lspci-v, and I will see all the information on the PCI bus. And you should see something similar if you have a PCI card that has the parallel port on it. Now, the reason I think that there are 2 parallel controllers listed here on the PCI bus is because that in the PCI card itself that I received, there is a flex cable included, and there is a parallel port, obviously, that's soldered on. And so those 2 ports are separate individual parallel ports, and this is what we see here on the terminal. So according to the LinuxCNC website, what we have to do is look at these I/O ports and figure out the correct address to use. And once we figure out that correct address, we just put it in the configuration files in LinuxCNC itself.
To figure out what the correct hex address to use is, I will have to hook up all the wires for the Z-axis on the second parallel port and cycle through all 4 addresses displayed on the terminal. When the Z-axis motor can be moved, I will know that I have the correct address.
Before changing over to the third address, I do want to show you how I'm doing this, how I'm changing the address itself, and basically it's just, a line of code. And so the second address was EE00, and the new address is ED00, and quotation marks, and there you go. And you save this, and you have a new address.
Now, as you add more and more to your machine, make sure you have a decent power supply, or else it will struggle to move and give you following errors. I actually had this problem and didn't realize it until later on. A weak power supply is another thing that's easy to overlook but can cause frustrating problems. I'm using this 12-volt, 3-amp supply, and it's working well.
Okay, this is extremely weird for me, because I just tested the Z-axis alone, so the X and Y-axis are not connected at all. I'm testing the Z-axis alone, and I'm testing it via the original parallel port that is directly on the computer itself. And the Z-axis works no problem. It has no problem going forwards and reverse. But the problem was that the Z-axis only went in one direction when all the other X and Y axes were connected. So the Z-axis would be fine going in one direction and then completely not want to go in the other direction for some reason. And I could not find out what the problem was. Now I realized that I'm using a PCI card, and I thought maybe that had to contribute to the problem somewhat. So I decided to isolate everything and just try the onboard computer parallel port, and the Z-axis works no problem with that. And then so what that leads me to believe is that somehow the PCI card is maybe not providing enough power to some pins that would control the direction of the Z-axis. It might, because the X and Y axis work perfectly with the Z axis connected. The X and Y axis are not affected at all by the Z axis being connected. So really, both the X and Y axes are connected directly on the parallel port that's on the computer. So the card that I wanted to control the Z axis with has a lot of problems with outputting signals. So I think what I'm going to do to try to solve this problem, because this setup won't work without the card needs to be there. But if the card is being a problem, then I think what I'll do is set it up so that the card will only accept inputs, and the card will have all the inputs from the sensors, from the encoders. And for the parallel port that is directly on the computer itself, I will set that up for all outputs. One thing I noticed in general, and this applies to all the axes that you're working with, is that you do need a ground wire present. You do need this ground wire that connects over to the negative side of your power supply.
So after I wired all sensor inputs to the PCI card and all the outputs to the other parallel port, every axis worked flawlessly. You can look up the wiring in the HAL configuration file once you have downloaded it, but I made a diagram on paper here too. You can see that there is actually one input on the other parallel port, and that's because I simply didn't have enough inputs on one card. This wiring configuration turned out fine though. Alright, now I'm going to explain how to get LinuxCNC on a USB flash drive. So, first thing that you want to do is go get the LinuxCNC ISO file. You go to the LinuxCNC homepage, go to download, and then just download the regular ISO file right here. And notice when it's downloading, it's over 1 gigabyte. So I recommend using at least a 2 gigabyte USB drive. I'm using a 4 gigabyte USB drive, so I'm fine. The next thing you'll need is a program called Rufus. Just type in Rufus on Google and the first link should get you here. It's a free download. So after you have your ISO file and the Rufus program, you open up Rufus and you should get a window like this. And in my case, my USB flash drive is already detected, but it's very important to make sure that it is your flash drive is selected. And just find your ISO file. Put the ISO file in and I guess rename it. And you can start formatting it. Once Rufus is done with your USB flash drive, you can take that flash drive out and put it into the computer that will control the machine. Once you plug it in and start the computer, it should give you some boot options. And I just select the first one and load into the live image. This loads the operating system on the RAM, so actually, once everything has loaded, you can take out the flash drive and everything will still run fine. Now what you want to do is go into the Applications menu, go to CNC, and LinuxCNC config picker. Then scroll down, make sure to check that Create Desktop shortcut. go down into parallel port and find etch servo. Click OK, and it will launch it, but you can exit out of this. So now what we want to do is go into the configuration files that you just created. Go to Home, LinuxCNC, Configs, and this is your configuration folder. Now, preferably you have another USB and you downloaded my configuration folder, and all you just do is drag and drop and overwrite the configuration folder that you just made. Alright, so now I'm going to explain how I take an image off the internet and convert that into G-code, which I can then put into LinuxCNC so my machine can draw it. First off, you want to have obviously an image to draw. And then I use 3 programs. I use Inkscape, I use NC Corrector, and I use MakerCam. Now MakerCam is actually in your browser, and we'll get to that in a second. But first off, you want to go into Inkscape. And all 3 of these programs are free, by the way. Drag your image into Inkscape. And don't worry about sizing it or shaping it right now. Just make sure your image is selected. Go to Path and go to Trace Bitmap. And this will give you a window. Make sure to turn on Live Preview so that you can see how your image is going to be traced. And you have different options here that you can play around with if you want it to trace based on brightness, on the edges, on even the color. So play around with these settings, and I usually go for edges. So that looks fine. And I'm going to click OK and exit out. And then what you should be able to do is drag your trace out like that. You can delete your original image and leave your trace in its place. Make sure it's selected. Make sure your trace is selected. Go to Path again and click Object to Path. What that is going to do is make paths out of this image, of course. And you can see that it worked because it says path 701 nodes in layer 1. And once you see that down here, then you know you're ready to save. So go to File, Save As. We can name it. Save as an SVG file somewhere. Alright, and you can exit out of Inkscape. So once that's done, you should be left with a file like this. Now, this is where MakerCam comes in. Here I have MakerCam open, and I'm going to do File and Open SVG File. And I'm going to put that file that we just made into MakerCam, and there it is. There's our logo. So now you want to just put it in a nice corner, like an edge, and resize it. So you can do Edit, Scale. Now, for this, it's helpful to know what the limits of your machine are. So I have everything set in inches right now. You can set it to centimeters if you prefer, but I just keep it in inches. And because I did test prints with my machine beforehand, I know that I can't really exceed 3 inches or 3 squares on the x-axis and the y-axis. That's basically my limit. To get an idea of your limits on your machine, though, you don't want to start off with pictures. I'm showing you a picture as an example right now, but in fact you actually don't want to start off with a picture. So before you even get into pictures, you want to start off with some test prints, and these test prints serve 2 important purposes. First of all, they give you an idea of the dimensions and the limits of your machine. because you don't want to draw outside of the page, or you don't want your picture to come out too small. And so you have to have a general idea of, when you're designing something in software, how it will come out actually on the page. And so these test prints are useful to give you an idea of your limits for your machine. The other thing those test prints do are make sure that your X and Y axis are in proportion with each other. And that's very important, because you don't want your pictures coming out squished or stretched or disfigured. And if your X and Y axis are not in proportion with each other, then your pictures will come out like that. So it's very easy to do this in MakerCam. All you have to do is go to Insert, and I like printing out a star. And so I just put the star in the corner like I do with the picture, print this out, and I measure each point and make sure that each point is equidistant from each other. And if it is, then I know my X and Y axis are in proportion with each other. And I also look to see if the star is 2 inches tall and 2 inches across, roughly, because the software is telling me that it's supposed to be roughly 2 inches across and 2 inches tall, but you never know once you print it out. You know, until you print it out, you don't know. So now back to our picture. First, you select everything and go to Cam and follow path operations. And you can leave the tool diameter as 0. And you are changing target depth, safety height, and step down. Now, your numbers will be different, but I know these numbers work for me. And to give you an idea of what you're doing here, when you change these values all to the same number, what you're doing here is telling the program how much you want the z-axis to move up and down. Now, I want the z-axis to move up and down 1/3 of an inch, roughly. And that's why I have 0.3 as my value. I click OK, and then I go to Cam again, and I select Calculate All. And that will calculate all the paths on the object. And then go to Cam one more time and do Export G-code. And export it. And name it. And save it. So once you're done saving your file, you should get something like this. And this is where NC Corrector comes in. So open up the file with NC Corrector, and immediately you see that our file is in this program, and you can see all the steps that your machine will take in order to draw this. And it's extremely useful because you can edit all this G-code, all the paths that it will take. So what we need to edit here in this instance is the fact that the z-axis moves up and then goes down below the origin. We do not want that. We actually want to raise this entire picture to make it level with the origin, with the 0, right? So this program makes it extremely easy to do that. And you just find the z-axis value that you want to change. You right-click on it, and then click Replace. And now it gives you a little box, and you can choose what to replace it with. And so we want the whole picture to move up to the origin, to be level with it. And so we're going to replace all the z-axis values of -0.3 with 0. So we're going to click Replace All. And right now it's replacing all those values with 0. And you'll see in a second it matched 73 and replaced them, and our picture moves up just like that. And it's extremely useful. It makes it extremely easy. And if there's anything else that you want to change, like maybe you want to exclude certain paths, then you can. we're not done yet. We still have to edit one more thing in this G code, and that is G64P0.001. And this G code is extremely important because it tells the machine to follow the exact path of all the lines. The problem I was having before I figured this out was that the machine was rounding all the corners and all the edges. And why that is has to do with the speed at which it draws. Because the machine wants to keep a constant speed, it compensates corners to maintain a set speed. And really, we don't care about speed that much. So I want it to follow the exact path, and that's exactly what G64 does. It tells the machine to follow your exact path, and it will compensate speed for that rather than compensate any corners. So once you're done with that, you can save it, and you're ready to put this file into LinuxCNC to draw out. And so to get ready for the print, I have to put that paper in. I put it in by jogging the y-axis via the keyboard, and so it just pulls the paper right in like a regular printer. And I'm also moving the z-axis all the way to the right. And with your machine, it might be a little different as to where the axes start off, where the origin is. Now, I move the z-axis all the way down till the pen is touching the paper. And as you can see, I have my image in LinuxCNC already, and what I'm doing here is homing the X, Y, and Z axis. And once I'm done with that, I can start the print.